Welcome to section 10.2. It's the line integral. There are two kinds of line integral. One of them is the line integral for scalar function. And then the second one is the line integral for a vector field. Okay. Today we're going to focus on line integral for a scalar function. One. Okay, what is the line integral for a scalar function? Well, in order to know what is going on here, we can follow the the integration. As long as you know how to do integration, you know what is going on here. Just do the surface here. So we're going to integrate over a curve C, x, y, z. Okay, let's say that we have a surface right here. So here come my surface, surface fxy. And then on the surface here, there's going to be a domain right here. So I'm going to draw my domain. Let's say this the domain. Domain of fxy. We know this domain by region D or region D. Well, we want to integrate over a curve instead of an interval. So now we're going to integrate over a curve. Let's say that we're going to have a curve C right here. Something like this. So of course, for every curve, you can parameterize the curve C. Okay, so when we integrate, what do we have? Well, we're going to have an area of something. I'm going to redraw my curve C up here. Integration over the curve C, fxy. This small part right here is ds. So fxy ds. This is the height. It's the height. And then ds is the arc length. So you can see that one as the width. And we just sum in a bunch of area over the curve C. So what we get is going to be this is the sample area. When we sum it over the curve C, we get the area of a curvy wall, fence or wall. Right? I'm gonna parameterize the curve C here. Okay, so if we parameterize it, the parameter is going to be t. And a lot of people just use t, so I'm going to be using a t, right? So our t is going to be a it's the vector. Xt, yt. And then t here go from some number a to some number b. If we parameterize it, then what is going on here? Then this integral is going to become the integral from a to b. It's now a closed interval, which we already learn how to do it. Fxy is going to be a f xt yt. Yeah. What do we say here? ds, if it's very small, that's why it's d. Is the root of dx square plus dy square. Oh, because everything is in terms of t, right? You can just many ways that you can do this. You can trick here is the multiply this thing by one over dt. 1 over dt here, 1 over dt times dt. So 1 over dt is going to be a dt square. So this one is actually equal to root of dx over dt square plus dy over dt square dt. So that is the ds right there. Dx over dy, dt square dy over dt square dt. Okay. 3 times of line integral of scalar function. Okay, here's the type 1. The first type is this just the integral over the curve C fxy ds. Everybody know that is the area of curvy wall, right? Fence or wall. Can project the area onto xz plane. So look at this area here. You push it onto the xz plane, right? then we have a integral over the curve C. Well, this xz here, it's going to be a, you can guess it, right? fxy integration with respect to x, right? fxy dx, right? You push it onto the xz plane. Right? Well, if project area onto YZ plane, then get integral fxy dy. You can integrate with the respect to x or respect to y. Okay. So here come a type 2. In type 2, we have fxyz ds. Well, fxy, everybody know, right? This is just the height. fxyz is not a height, it's density. Well, when you take density, you multiply by a very small arc length, you're gonna get a small arc length. It's just like an area. You're gonna get a mass of a thin wire. So this thing is mass of a thin wire. And the thin wire is the curve C. That thin wire. Okay. One more. Type 3. In type 3, well, you just do the line integral of ds there, which you already know, right? This the length of a thin wire. Yeah. Curve or a thin wire theorem. Sometimes we don't have one curve, right? Because we can stick a bunch of them together. So if C is a union of finite smooth curve C1, C2, Cn, then the integral C fxy ds is equal to the integral of C1 fxy ds plus integral of C2 fxy ds plus plus integral of Cn fxy ds. We need this theorem to do the example. Here comes the example. Evaluate integral C 2x ds, where C consists of the arc C1 of the parabola y equal x squared from 0, 0, 2, 1, 1, and C2 and followed by the line C2 from 1, 1, 2 to 2. Uh, 1, 2, 1, 1, 2, 1, 2. Sketch C and parameterize. I go from 0, 0 to 1, 1. So it's a parabola. Okay. And then from 1, 1 to 1, 2 is the straight line. Make sure you put the arrow because the arrow is indicated direction. It will help you to parameterize distance correctly. X equal t, then y gonna be a t square. Here we don't have to play around with the RT, right? Not yet. The vector RT right here is gonna become very handy when we get to the vector field. For now, we can parameterize in this one. And where does t go from? 0 less than equal t, less than equal to, go from 0 to 1, so it's going to be 1. Okay, so now I have to do parameterize C2. Okay, well, C2 is just a straight line, right? Most of you already know how to parameterize a straight line, but if you don't, it's just a reminder here. So this is the kind of redraw this thing here, just a little review on parameterize any straight line. Well, straight line is connected by 2 points, right? So you're gonna have a P is gonna be a X naught, Y naught, Z naught. Q is the X1, Y1, Z1. Right? Then from here you see that PQ is gonna be a vector. Is the vector RT. You can parameterize it by multiply by 1 minus t. Hopefully you remember this from your previous class. Multiply to the first point, X naught, Y naught, Z naught, plus t, X1, Y1, Z1. Work it out, and then you see that we get X naught plus t, X1 minus X naught, Y naught plus t, Y1 minus Y naught, Z naught plus t, Z1 minus Z naught. Okay. From here we see the X, the Y, the Z. equal to x naught plus t x1 minus x naught, y is equal y naught plus t y1 minus y naught. Z is equal to z naught plus t z1 minus z naught. That completely makes sense. For t has to be from 0 to 1. So when t equal to 0, we have a x naught, y naught, z naught. When t equal 1, we have x1, y1, z1. So x here is going to be you can follow, right? It's x naught plus t x1 minus x naught. So x naught is 1, and then x1 x naught, they're the same, so here it's just 1. Y is the y naught is 1 plus 2 minus 1 is 1, so 1 plus t. Oh yeah, z1 minus z sub 0, I think. Oh yeah, I write so fast that z0. Okay. It's going to be 1 plus t, and then 0 less than equal t less than equal 1. Step 2. Set up integral. And evaluate. Well, the integral is already there. Yeah. Integral c 2x ds. That I'm going to use the theorem. Then I'm going to parameterize it. Right? It's theorem. C1, C2. Okay. Next is going to be a parameterize. Yeah, you got to go to theorem, then you parameterize. One step at a time. So look at the C1 here. Where does the t go from 0 to 1? And then 2x is t. Let's see. So 2t. ds, well, might as well do the ds. So if you remember that, dx over dt square plus dy over dt square, square root, that one, that's ds right here. So I'm gonna do the ds there, save myself some time here, right? 1 square plus 2t square dt. So that would be root of 4t square plus 1 dt. Okay. Root 4t plus 1 square dt. So for C2, 0 to 1, 2, x is 1. And then for the ds here, it's going to be a root of 0 square, right? Because you got to take the derivative with respect to t and then you square it. So 0 square plus that is the 1 square dt. So we just have dt. Oh, ds is dt. How nice. Okay. So you do the u sub here. Let's see. What do we get here? So there's gonna be 8t, right? 8t is gonna be 2t over 8t, so it's 1/4. And then it's gonna be a half plus 1 is 3 over 2, so time 2 over 3, 4t squared plus 1, 3 over 2, 0 to 1. Oh, and this one right here is just 2 times 1 minus 0. Okay. 1 over 6. Four times 1 plus 1 is going to be 5. Huh? And then 4 times 0 plus 1 is going to be 1. So 5 minus 1. Oh, so it's 5, 3 over 2 minus 1. Yeah. Plus 2. Okay. Here come another example. Okay. Done with the sketch. Now it's time to this is the curve C here, right? But it is part of the unit circle. So you don't actually parameterize anything, right? Sometimes you don't have to parameterize anything. Can anybody tell me why you don't have to parameterize this thing here? We know that area is integral over the curve C. Fxy ds. Fxy, well, it's the height, and then ds is the width. The height here is 2, right? And then the width here is just look at this thing here. C ds. So this is exactly 2c ds. So what is this? This arc length of the curve C. Well, we know the length of the curve C is just half of the half of the circle. So it's gonna be a half of 2 pi r. See. Oh, and then well, we know R is 1 because unit circle. So in the end, it's just going to be a 2 pi